Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome back. We are going to talk about conformational isomers. What are conformational isomers? Let's take this molecule for example. Okay, we draw it like this with lines, but actually sigma bonds are nothing but electron clouds, fuzzy electron clouds, not even like solid like here, it's just a fuzzy electron cloud, okay, which means you can rotate about these bonds. There's really just nothing but a fuzzy electron cloud in here, okay. So when you rotate this molecule, each time you rotate, there's a different spatial arrangement between the atoms within this molecule. Or you could have groups of atoms. Each one of this is called a conformer or conformational isomer. Sometimes they even call them rotamers. Again, these are going really, really fast and you can create thousands of this. Now, every time you change the spatial orientation, the interaction between these electron clouds, which we call bonds, also change. So therefore the energies will change and the stabilities will change. So conformational isomers are molecules that have different spatial orientations of atoms or groups of atoms due to rotation about a sigma bond, okay, due to rotation about sigma bonds. All right, so when you rotate them, the dihedral angle changes and therefore the energies and the stabilities change to their relative spatial orientations. All right, let's look at some examples. We did some conformational isomers of ethane, propane. We're going to do some for butanes. So let's look at butanes. Here's a 4-carbon chain. So we looked at ethane, and if you put a carbon here and a carbon here, that'll be 4 carbons. So we're going to rotate butane and see how it is. Now I have kind of put these hydrogens as balloons because just to show you that they're nothing but electron clouds. So these are also CHs, but I haven't put balloons for those. I've just put it over here just to emphasize the steric interactions. Okay, let's look at a butane. So butane is basically 4 carbons. And so if you draw a condensed structure for that, it's going to look like this. And then we can draw an expanded structure for this. And it would depend on which sigma bond you're rotating for the energy graph, because each of this would give you different conformers. So let's say we're going to rotate the middle C2, C3. So C2, let's say, is this, and C3 is going to be your circle. On the 2, there are 2 hydrogens and a methyl group. And on the 3, there are 2 hydrogens and a methyl group. So pretty much you're going to do the same thing on this side as well. Hydrogens and a methyl group. Okay, so this is 3, 1, 2, 3, 4, and it says look through C2, C3 and draw the energy diagram. So let's look at it. So here is your, let's say number 1 is these yellow or gold color balloons. Number 2 is the yellow. Number 3 is the blue, and number 4 are these teal color balloons. So when you have them like this, you can see that these balloons, these electron clouds, are butting heads. You can almost see a lightning spark going out. So this is a very, very high energy conformer. So we definitely want to get out of this. But for the calculation of energies, when you have a methyl, you have this steric. And then we also have this carbon-carbon, which is like quite a bit of electrons here, and carbon-carbon pushing and getting into this position where your anti-bonding orbital is stabilizing the bonding orbital on the carbon-carbon bond here. That's the torsion. So you have steric and torsion. And both of those together, the torsion, that's like pushing this apart, and the steric here is 11. If it gets out of the way, is it all safe? Well, the steric decreases slowly, and since we are drawing in 60-degree increments due to the computational programs, the way they programmed it, this 60-degree angle would still have some steric. It's not all gone away. You can see they're still quite close. So that's called a gauche steric interaction, and that's 3.8. When you go away from that, you have a CH that's eclipsing a CH3. The hydrogens are kind of minuscule. So there's no electron cloud bumping here. So there's no steric. However, the CH bond electron density and the CC bond electron density are repelling, and they'll be much better off with the anti-bonding orbital stabilizing it. So that's torsion. So you have torsion here, and that's 6 kilojoules per mole. And you also have the torsion. This hydrogen and this hydrogen here have no steric, but the CH and the CH bonds have torsion. So they want to get away. And so you will have this. When you have this, well, there's nothing really eclipsing, and there's no gauche, and there's no torsion. It relaxes. So we are going to do an energy graph going from, we can start anywhere. You can start here or here, but let's say this is your highest energy. We'll set this dihedral angle as 0. So this is your eclipsed gauche. This is also an eclipsed, but it's not as bad. This is anti, because they are opposite sides. This is another eclipse. This is a gauche, again 60 and 300. You have 2 gauches here between these 2 methyl groups. And this is a syn. It is totally unhappy in syn. Let's draw it out. Let's go over to this. This is going to be your syn. Your methyl and your methyl are going to be facing each other. So I'm going to rotate, let's say, your front carbon and keep your back carbon the same. I could have very well chosen to do the opposite. We'll keep the back carbon and rotate the front carbon. All right. So your back carbon, let's say, has got CH3, HH, and then your front carbon is going to rotate along. So this is your front carbon, is your dot. Your back carbon is always, back meaning you're looking to, where they will say look through 2 carbons. Okay, in this case, C2, C3. Even when you're doing the computational program, you can collect data for those 2. So here's your methyl, eclipsing that, so you can draw it parallel to that. So here's your CH3, and then that is going to be your CH hydrogen, starting with the highest, hydrogen, hydrogen. Let's do the 60-degree angle here. This is going to go 60 degrees. All of them are going to rotate 60, so you will have a gauche interaction here between this methyl and this methyl, just like this. Then you're going to rotate another 60 degrees, so you're going to go all the way here to a 120. So you're now going to be parallel, this methyl is going to be parallel to this hydrogen, and you are going to have the other hydrogen sticking up. Another 60 is going to bring it all the way down here, 180 from your previous position. So your hydrogen methyl is going to go down. So this is now here, and now you're going to go down like this. And your two hydrogens are going to be sticking up. Another 60, and you're going to be parallel to this CH. So this is another 60 here. And then your hydrogens are going to be sticking up and on the side. And then you're going to go another 60, and you're going to be your neighbor. Your neighbor is going to be the methyl. Gosh, kind of an awkward peeking into your neighbor kind of thing. Gosh. And then you go back one more 60, and you will go back to your A, B, C, D, E, F, and then you go 60 degrees A, B, C, D, E, and go on and on and on forever. Let's calculate the energies based off of the chart there. So this we already said was 11. So let's do our calculations here. This is 11, and kilojoules per mole, understood. This is going to be HH is 4 and 4. So this is going to be 19 total. This has got no hydrogens eclipsing, no eclipses because it's a staggered. And by the way, this has a name, SYN, because that's going to be the most unhappy orientation, highest energy. This one is kind of awkward because you have neighboring groups peeking into each other. Gosh. And back again, you're eclipsing the bonds back to back. And so therefore, that is going to be just an eclipse. This is also a SYN eclipse. They just didn't bother to give this another name. It's just an eclipse. And so CH3H is going to be 6. This is going to be CH3H, another 6, and a 4. So that's going to be 16. This is going to be 3.8. Write the number down here, 3.8. And over here now, this is going to be back again, another staggered, and that's going to have all the way down here, but this staggered is unusually stable. There's no neighboring methyl groups for either one, so this is called the anti-staggered. And so that is going to be 0. Nothing is eclipsing. Back again. So this is going to be your energy minima. This is where you're going to live most of your life out, like vegging in front of the TV on the sofa. That's your energy minima. Okay. Now, well, you can't stay there forever. Get back to work. So now here you're going to have back again a eclipsing interaction here. This is 6, 6, and 4. That's 16. This is a very symmetric molecule, so the energy graph is also going to be symmetrical. This is just an eclipse. And then back again, kind of uncomfortable next to your neighbors here, steric. So that is going to be a gauche interaction. So that is 3.8. So this is 3.8. So we can go in and write down these numbers here. So this is the potential energy graph for this molecule with time, or in this case, with angle. So you're going in 60-degree increments. So let's say this is your 0. This is where you start. Then you move 60, 120, 180. That's the best anti. Then you go back to 240, 300, and I don't have space to write it. I put 360, which is again going back to the original eclipse. So here you're going to have 19, and that's literally the highest over there. This is 3.8. And this is 16. And then you're going to have nothing, 0, due to the non-bonded interaction. Potential energy due to non-bonded interaction. I'm going to put NB. Because there are molecules other potential energies. So again, 16 here, and then 3.8. And then again, it's going to go back again to your 19 and start all over again, right? So let's draw it out. Graph. So let's go up and down, vertical, and I'm just going to say repeat. That's just showing you different conformers at 60-degree increments. You can have an infinite number of conformers if you draw all of them, but we're just drawing 60-degree increments. So that's for butane. So the energy minimized here. So if you take a snapshot of this butane, most of the time, this is where you're going to catch the butane. Lying down on the sofa, watching TV, energy minima. Maybe munching on some chips and beer. Let's look at another molecule. Well, let's grow it a little bit. What if one of these methyl groups had a neighbor? Let's say you have a methyl here. Let's put a branch and see how that's going to be. Let's take our methyl group here and put a branch on it. Is it going to be a lot different? So this is a 2-methyl-butane. This is a butane. You can have 2-methyl-butane. Or you can do one for 2-3-dimethylbutane, or you can do pentane. The methyl and ethyl energies are not very different, but they do have, when you have ethyl groups, it's slightly different. Because the methyl on the ethyl can be pointing away. So here, well, let's rotate the back carbon this time. So this is carbon 1, 2, 2's got a methyl, carbon 3, and then carbon 4 is this brownish color or gold balloons at the back. So let's do a back rotation, and here it is. So here are your 2 methyl groups in front, and this is going to be probably the worst, eclipsing this, bumping into this. This is what the molecule dreads the most. So it's going to get out of the way and then go over here. But it's still, gosh, then it keeps going over here. Now it's eclipsing with this CH. There's no reprieve for this molecule. Goes over here, got away from the blue balloons, but now it's neighbors with this methyl. Okay, well, it's got to go through this again, really bad, steric interaction. Then over here, 2 neighbors kind of squeezing it, gauche interaction. And then, well, let's try to get away from that. Nope, another eclipse, where you're literally, the electron clouds are butting heads and fighting it out for space. So again, it goes away and does the same thing. So let's draw these out, just because we make you do it. So we have to kind of show you, how to do it. So let's again look through 1, 2, 3, 4, 2, 3. Look through C2, C3. So the C2 will be a dot. C3 is going to be your circle. So we're going to keep the front the same just for practice. So let's draw it out. It always helps. That way you don't miss any hydrogens. So this carbon is C2. You have CH3 here. And then you have a CH3 here. And then you need to have another hydrogen. You move over here. C3 is going to have 2 hydrogens. CH2, and then you'll have a C4 on that, which is a CH3 group. So that is going to be, you can label either this or this one, and you'll have to look through here. I mean, this is difficult to draw right away from this line diagram. You could probably draw a condensed diagram before you do the line, but you would see after some time, you would be able to go from here to here. So 2, 3, what do you see when you look at 2? You're going to see 2 methyl groups branching out. So let's draw them. So over here, CH3, and on the left-hand side, let's say CH3 and H. Now, what if you drew this flipped? Doesn't matter, because it's going to be symmetric. Now, at the back, you're going to have C2 with 2 hydrogens and a methyl. So let's start with something that's kind of not that great. CH3, H, and H. Okay, that's kind of an eclipsing interaction. You want to get away from that methyl, so you go 60 degree off, 60 degree rotation. For all of them, let's try to keep the front carbon the same and just rotate the back. So let's rotate that 60, so you can see there's a gauche interaction here. So that's methyl, hydrogen here. Everything rotates 60, right? It's like your steering wheel. Now another 60, this is going to come all the way here, down over here. So another 60 degree angle is going to put that methyl eclipsing with this hydrogen. And here you're going to do the same thing. So this hydrogen is then going to go all the way here. I'm going to draw it here just because. And this hydrogen is going to go all the way here. Another 60. And because, well, it's a hot day, you got a lot of energy. These molecules absorb in the microwave region and rotate. And so they have plenty of energy there from the sun's energy during the daytime and night, because the sun really doesn't go anywhere. You just don't see it. So it's happening all day and all night. So here's your hydrogen at the back. And then this is your other hydrogen. Well, got to go over here because we just have all that energy to expand. So you have a hydrogen eclipsing, and this is going to eclipse with this. And so this is going to be here for this one, opposite. Then the 2 methyls are going to eclipse, and then now you're going to do in between. So this methyl is going to be in between these 2 methyl groups, and then the hydrogens are going to go 60 degree increments to the side and over here. Then back again another 60, and you would go to your home base here. So let's say this is A, G, H, I, J, K, and then again G. And it goes all over again, repeat. Let's calculate the energies of these guys and see which is the best position for this molecule to recline, maybe get a shut-eye. Let's say methyl, 11, methyl hydrogen, 6. And here's a hydrogen, that's 4. So that's about 21. I mean, some books have put it as 22.7 or something, but we're just doing an approximate, about 21. So this is potential energy for non-bonded interactions. So if it's 0, doesn't mean the molecule doesn't have potential energy. Of course, if you burn it up, you're going to get a lot of energy coming out of it. Butane's your cigarette lighter fuel. And so you are going to get a lot of potential energy, but this is just a non-bonded energy. And this is the angle of rotation, theta, or dihedral angle, the angle between, let's say, these bonds. This is 0, this is 60. That's the dihedral angle. So over here, this is going to be 21. Let's say this is going to be a gauche interaction here, nothing else. So that's 3.8. That's pretty good. So this is 3.8 total. This is going to be hydrogen methyl torsion, 6. Hydrogen methyl torsion, hydrogen methyl torsion here. That's about 18. Like something like 19 point something, but this is kind of approximately following these. Let's go back here to our gauche interaction, 3.8, and that's about it, which is really nice. And let's say over here, back again, eclipse, methyls 11, hydrogen methyl is going to be 6, hydrogen is going to be 4, so that's 21. Just like G. And here you have a methyl-methyl gauche interaction, methyl-methyl gauche interaction on both sides. So there's a 3.8 here and a 3.8 here. That's going to be 7.6. This is all in kilojoules per mole. Kilojoules per mole. And here's your angle. So let's say 21, 3.8. There's no 0 here. So you really cannot have kind of a deep sleep state. It's constantly having some kind of strain. 3.8 again, then 21, then 7.6 here. So these are also kind of approximate. So 21 going to 3.8. And then going to 18, and then going to 3.8 again, going to 21, and then 7.6, and go back again when it goes all the way back here to G. That's going to be G. So you're going to go back to 21, start all over again. So now if you're like in the pharmaceutical industry, trying to find the energy minima, that's where you're going to have to, trying to mimic that molecule there. That's your energy minima. This whole exercise is to find the energy minima. That's your energy maxima. So you take a snapshot of this molecule, you're probably never going to see it here. So it gets away from the energy maxima real quickly because of all the torsion and steric. It's really unhappy there. And it lounges around here. It's probably got a lazy boy sofa in its basement, and this is where it's kind of watching TV and watching and catching all its basketball games and football games in the energy minima. That's where you want to be. All right, guys, so I'm going to see you soon. If you have any questions, let me know, and I will talk to you soon. Bye.